Hello, bachcho. Have you ever wondered why your blood is red, leaves are green, or why copper sulfate solution looks so fancy blue? It's not magic, it's coordination chemistry at work. A coordination compound is simply a central metal atom or ion that has loyal friends called ligands sticking to it through coordinate covalent bonds. Think of the central metal as the class monitor, usually a transition metal, and all the ligands as the students happily donating their pens. I mean, electron pairs to help him out. The coordination number is just a fancy way of counting how many students, donor atoms, are directly bonded to the monitor. For example, in cobalt hexamen, written as open square bracket CONH36 close square bracket 3+, the monitor cobalt has 6 ligands lined up. And trust me, coordination compounds are not just classroom gossip, they are big shots in biology, industries, and even medicine. Now, bachcho, meet the real VIP area of these compounds, the coordination state. This is the central metal and all its ligands enclosed inside square brackets, like a celebrity group inside the green room. But wait, every VIP party has bouncers outside, right? Those are the counter ions. They balance the charge but don't really get to dance inside. For example, potassium hexacyanophorate is written as K4 open square bracket Fe N6 close square bracket. Inside the bracket, iron with 6 cyanides is the coordination sphere. Outside, the 4 potassium ions act as the counter ions, politely waiting like parents outside a school gate. Together, they form the coordination entity. So remember, sphere inside, counter ions outside. Don't mix them up, or else you'll be like the student trying to sneak into the staff room. Alright, let's talk about ligands, the loyal fans of the central metal. Ligands donate electron pairs, but they come in different types. First, unidentate ligands, which can only hold the metal with one hand, like chloride ion, Cl- or ammonia, NH3. Then come the bidentate ligands, holding with both hands, like ethylene-diamine, also called N. And then the superheroes, polydentate ligands, which grab the metal from multiple sides. EDTA is like that overprotective friend who won't let you go. It hugs the metal from 4 different places. When these ligands form a ring around the metal, we call it a chilte. Think of a crab claw gripping tightly. Once it catches, good luck escaping. That's why chelating ligands make coordination compounds much more stable. Now, bachcho, chemistry is not just about bonding, it's about fashion too. The way ligands arrange themselves gives coordination compounds their geometry. We call this arrangement the coordination polyhedron. If the coordination number is 6, you get the classic octahedral style, like in cobalt hexamen, open square bracket CONH36 close square bracket 3+, where 6 ammonia ligands arrange neatly like chairs around a dinner table. With coordination number 4, you might get a tetrahedral geometry, like in nickel tetrachloride, open square bracket NiCl4 close square bracket 2-, which looks like a tripod with an extra leg. Or you might get a square planar geometry, like in platinum tetrachloride 2-, open square bracket PtCl4 close square bracket 2-. Honestly, it's like the metal is deciding whether to sit in a circle, a square, or a pyramid. And yes, just like a new haircut changes your vibe, geometry changes the color, magnetism, and reactivity of these compounds. Okay, time to bring in the maths, but don't panic. The oxidation state is simply the effective charge on the central metal after considering the charges of ligands. For example, in iron tetracarbonyl, written as open square bracket FeCO4 close square bracket, carbon monoxide is neutral, so the oxidation state of iron is 0. Now, the bonding here is quite romantic, The ligands donate electron pairs to the metal through coordinate covalent bonds, like saying, "Here, take my electrons, I trust you." This bonding is what makes complexes stable. In industry, this concept is super important. Catalysts, like platinum and palladium, change their oxidation states during reactions, like chemistry's own quick-change artists. Imagine them in a magic show, switching outfits instantly while still keeping the audience entertained. So, bachcho, let's quickly recap before the bell rings. Coordination compounds are formed when a central metal bonds with ligands to make stable complexes. We learned terms like coordination state, counter ions, ligands, coordination number, and oxidation state, all fundamental for understanding these compounds. Ligands can be unidentate, bidentate, or polydentate, and some, like EDTA, hug the metal so tightly they never let go. Geometry decides whether a compound is octahedral, tetrahedral, or square planar, and this geometry affects properties like color and reactivity. Finally, we saw that oxidation states and bonding make these complexes the real workhorses in biology, industry, and even medicine. So next time you look at a colored salt or think about hemoglobin carrying oxygen in your blood, remember, it's coordination chemistry running the show. Chemistry isn't just equations on the board, bachcho, it's the backstage manager of life's biggest drama. See you next class with more chemical adventures.